Okay, so what we're going to do today is nowhere near as complicated as what we did last time. So you can sort of take it easy. We're introducing another field, right? The so-called complex numbers. Okay, so normally when I do this, unfortunately you've all read the material already, but normally when I do this I say let's introduce a field on R2. We're going to take R2 and make a field out of it. And I don't tell anybody that it's going to be the complex numbers, right? But then in the end it turns out to be the complex numbers. So let me just pretend that you don't know what we're doing. And say, okay. So let's take R2, right? And let's let F, this field, be as a set. Well, it's going to be all these numbers, these pairs of numbers, right? So pairs of ordered pairs of real numbers. Okay, and we introduce we define plus on this field by saying that the sum of two of the elements is defined component-wise. Right? So you say, okay, this is going to be A plus C, B plus D. Okay, and that's going to be our sum, right? That's our sum operation. And we also define a multiplication by saying that AB, the product of two things, is going to be AC minus BD, AD plus BC. Okay, and so then we have this theorem that this thing with the plus and the dot is a field. Okay, and what's going to be the additive identity, right? What's going to be the additive identity? What's the thing that you add and it doesn't have any effect?
Zero.
Well, 0, 0, right? 0, 0. So 0, 0 is going to be the additive identity. Right? 0, 0 is the additive identity. Right? And you recognize this is just your vector addition from whatever class you had before, right? This is just the addition of vectors, right? You have some guy AB, you have some other guy CD, right? And the sum is just going to have the sum of the right. The sum is just going to have the sum of the you have A plus C and B plus D, right? A plus C, B plus D. Geometrically, right? This is something that you're familiar with, right? So the addition is something that you've seen before. The multiplication is maybe something that you haven't seen before, right? So what does it mean when you take this vector AB and you multiply it by CD, and you get this AC minus BD, AD plus BC, right? What is that geometrically? In fact, it does have a nice geometric interpretation, which I might just gloss over later. Okay, so, and what turns out to be the multiplicative identity?
1, 0.
1, 0, right? 1, 0 turns out to be the multiplicative identity, right? Because if you take AB times 1, 0, right, where you get AC, which is A, minus BD, which is 0. You get AD, which is 0, plus BC, which is B, right? In other words, you get AB back again, right? Right. And so, you need to prove a bunch of, in order to prove that this thing is a field, right? You need to prove all those axioms, right? So, for example, if we look at if we look at CD times AB, right? What do you get? Well, you get CA minus DB, and then CB plus dA. CB plus dA. Right? And you notice that that's the same thing as AB times CD. Right? And so the commutative multiplication is commutative. Right? So, right. Right. So you prove all these things. You know, it's pretty straightforward to just run through all the properties and show that they are satisfied. And maybe the only interesting one is the existence of the multiplicative inverses. Right. So multiplicative inverses. So you say, well, if AB is non-zero, then it turns out that 1 over, this way, turns out that A over A squared plus B squared, comma, negative B over A squared plus B squared is the multiplicative inverse of AB. Right? I hope you see that, right? Because if you take AB times A over A squared plus B squared, negative B over A squared plus B squared, you see what you get, right? You get AC, which is AC, so you get A squared minus BD, right? So it's going to be plus B squared over A squared plus B squared. And you get AD minus, AD plus BC, which is going to be 0. Right? In other words, you get 1, 0. Okay, you get the identity element. Okay, so right, so you know, R2. If you take R2 and then you put on it this addition and this addition and this multiplication, then then it turns out to be a field. Okay, so it's not particularly exciting. Okay, one thing that's nice about this field is that R is a subfield of it. Right? So via the map, let's say phi goes from R into the field, taking x to x comma 0. Okay. So there's a way of embedding R into this field F. Right, you take right, so here's R and here is F, right? Here's R and here's F, and you basically stick R inside of F by saying any number. If I take the number x, then I map that to x comma 0, right? Anybody x here corresponds to x comma 0, right? The number 0 would go to 0, 0. The number -1 goes to -1, 0, etc., etc. Okay, so I can take R and I can stick it inside of F, and this is in such a way that the operations of R correspond to the operations of F. right? So the operations are preserved, right? In such a way that the field operations are preserved, right? If I add two numbers here, then that corresponds to adding the corresponding elements here. If I multiply two numbers here, that corresponds to multiplying these guys using the F multiplication here, right? Right. So, right, if I have X and Y here, and I add them together, that's the same thing. I'll get the same thing as if I added X0 and Y0 over here, right? I'm going to get X plus Y comma 0, right? The sum of these guys, X0 plus Y0, is going to be X plus Y comma 0, right? Right? Which is, so what we're saying is that the map of X plus the map of Y is the map of X plus Y, right? That the addition, you can either add them before and then map them over, or you can map them over and then add them afterwards. Okay. Similarly, right, if I multiply them and then map them over, it's the same thing as if I map them over and then multiply them afterwards. Okay. So there's a preservation. When I say that there's a preservation of the field operations, this is more formally what I mean. So R literally exists as a field inside of this new field F. Okay. Right. Okay. And then you say, okay, well, right, so what's 0, 1 times 0, 1? What happens when you multiply 0, 1 times 0, 1? You get AC minus BD, right? That's negative 1. And you get AD plus BC, which is 0. Right? So here's the point 0, comma 1. What happens when we multiply it by itself? Well, we get negative 1, 0. Okay. Well, this negative 1, 0 corresponds to negative 1 in the real numbers, right? Which is to say negative 1. If we're thinking about the real numbers, this is negative 1. And so you see that in this field, there's something whose square is negative 1, right? And so we call this thing I, right? We call this thing I, right? So this mysterious field has a square root of negative 1, right? So we call this thing by the letter I. Okay. So it's in this way that you take the real field and you extend it to a two-dimensional field that has square roots of negative numbers. Okay. Okay. Of course, 1, 0 is the analog of the real number 1, right? 1, 0 is the analog of the real number 1, and so every element AB, so every AB in this field, which we should now call C, the complex numbers, right? In this field can be expressed as so you can write AB as A times 1, 0 plus B times 0, 1, right? So everybody in the field can be written as A times 1 plus B times I. and this is what you're used to from, I don't know, junior high school or whatever. High school, whatever you saw. I don't remember. It's been too long.
Wait, question.
Yes.
So if you wanted to prove that some field is a subfield of some other field, is it enough to just define a mapping that preserves the field operations?
Well, it should also be a one-to-one mapping, actually. Yeah.
Does it have to be onto, or?
It has to be a one-to-one mapping, but not, right, it's not onto. Right? It's an injective map, so a one-to-one map. Okay. So this thing that we're dealing with, this f that that we've introduced, is actually your old friend, the complex numbers, and that's what we'll call it from here on in. Okay. So just for entertainment, I'm not going to prove this, but how does complex multiplication work? It's actually has a kind of nice geometric meaning. So if I have a complex number z and I have another complex number w, where is zw? Where is zw in the complex plane? Well, the way you figure it out is you draw the unit circle. Okay, so let this be the unit circle here. Okay, let this be the unit circle. And what you do is you take this triangle to the end of z and back to this point on the unit circle. Sorry. Okay. You take that thing, okay, and then you draw the similar triangle with w as corresponding to this length here. Okay, so this length from 0 to 1. Okay, so you take this w as that, and you draw the similar triangle. Okay, and then this point turns out to be zw. Okay, so that multiplication we saw earlier has a nice geometric interpretation. You add the angle, right? So what are we doing? We're adding on the angle of z, right? So you take w's original angle, but you add on the angle that z made with the positive x-axis. Okay, and then you scale w by the length of. You multiply the length of w by the length of z, right? And you get this thing, zw. Okay. So take a course in complex analysis, and this will become obvious. Or just you can read this in like 10 minutes or 5 minutes or something if you look on the internet. Okay. Okay. So complex numbers, you've probably seen it before, but let me just introduce everything so that all the terms are down. Okay. So some terminology. You have some point in the complex numbers. People usually denote the point by like the letter z or w, or commonly zeta. Zeta is a pretty common thing to use in the complex analysis. Zeta. For variables, people tend to use zeta and z. Okay, so you have some point A, B, right? This is A, B, which is A plus BI, right? So let's say here's the number 1, and here's the number I, right? This guy is A times 1 plus B times I, right? And so we call the real part of Z is A is called the real part, B is called the imaginary part, right? Real part, imaginary part. Real part, imaginary part. There's something called Z bar, which is defined to be A minus B. It's called the complex conjugate of Z. Okay. So in other words, you take the imaginary part and you flip it over. Okay, you take the imaginary part and you flip it over. So here I've got my z, right? Z bar is going to be across the, is going to be reflection of that across the real axis, right? So this is called the real axis, imaginary axis, right? So z, the original point, z bar, your complex conjugate. Okay, there's some simple properties of the complex conjugate. First off is that if you take a sum and then take the complex conjugate, so you take two guys and you take the complex conjugate, what do you think that's going to be equal to? The sum of the individual complex conjugates, right? That seems pretty clear, right, geometrically, right? If you add two vectors and then you flip them over, you get the same thing as you flip those guys over and then add them, right? If you take a product and then the complex conjugate, then what do you get? Same sort of thing, right? You're going to get the product of the complex conjugates. Again, that could be argued, you could think about it geometrically, or you could just work it out as numbers and see that you get the same thing. C, if you take the sum of a number and its complex conjugate, what do you get? So I take this guy, right? I take this guy, and I add on to it that guy. Right? What do you get?
Real part of 2z.
You get the real part of 2z, or twice the real part, right? Twice the real part is twice the real part of z. Right? Same thing, right? If I take, what am I going to say next? Subtraction, yeah. If I take z minus z bar, well, what do I get? 2 times just about right. You get, so you get 2 times I times the imaginary part. Right? 2 times I times the imaginary part of z. Okay, right? And the last one, if I take z times z bar, you notice that z times z bar, well, a times b, a times negative b, right? What am I going to get?
A squared.
I get a squared. So a squared, I get plus b squared, right? And then I get 0. Right? I get a squared plus b squared. Right? A squared plus b squared. Okay. Okay. And this actually answers one of your questions. So somebody sent in a question, like, how do you know what the inverse, why do we choose that term for the inverse? Remember what we chose for the inverse? It was 1 over a squared plus b squared, a minus b, right? A over a squared plus b squared, negative b over a squared plus b squared, right? Now you see why that was the obvious choice, right? Because this is 1 over z bar, right? If you multiply this thing by z, you get 1. Right? Multiply this by z, you get 1. Right? So this is what. That's how we got the. That's how you get the inverse of a complex number. Right? Well, z bar over z bar. Close your eyes for a second. Should I go faster? Raise a finger if I should go faster. Raise a finger if I should go slower. Okay, thank you. Okay, so most people are okay. I'll probably just stay at this pace. A couple people want to go faster, which is nice. But okay. Okay. So other things that are other important ideas. One is the absolute value for complex numbers, also called the modulus. But it just means absolute value. So, right, for any z in the complex numbers, we define the absolute value as the square root of z times the complex z times the complex conjugate. Okay. Notice that we know that such numbers exist and are unique. Right, by the work we did last time, right? Because you're going to get this says the square root of some positive number, right, or some non-negative number, right? And what we showed last time was that in the real numbers we do have square roots. We do have unique square roots of positive numbers. Okay. Properties of the absolute value. Some are pretty straightforward. Right, and right. So notice that this is the same thing as the vector definition of magnitude, right? Right. If z is a plus bi, this is the square root of a squared plus b squared, right? Which is what you saw back in Calc 3, in multivariable calculus, right? This is the distance to the origin, right, of that point. And if this point is a comma b, right, the distance to the origin is a squared plus b squared to the 1/2, right? That's the same thing as this, z bar to the 1/2. Okay, so there's a geometric meaning to this magnitude. So, so there are a bunch of elementary properties of the absolute value for complex numbers that correspond to the same things for the real numbers. The absolute value is always bigger than 0, right, for all z that are non-zero. 2, the absolute value of the modulus is the same thing as the absolute value of the original guy. It's sort of obvious. C, the absolute value, the modulus of a product is the same as the product of the moduli. D, the absolute value of the real part is less than or equal to the absolute value, the modulus of the complex number. And E, the modulus of a sum is less than or equal to the sum of the moduli. Okay. What's the name of this last thing? Triangle inequality, right? Triangle inequality, right? And now that we're in the complex numbers, it really does look like a triangle inequality, right? Back when you learned it in the reals, maybe it wasn't so obvious, right? So here, you've got z, you've got w, right? This point is z plus w, right? z plus w. And what it's saying is that the length of z plus w, right? The length of z plus w is less than or equal to the length of z plus the length of w. Right? In other words, the length of one side of a triangle is dominated by the sum of the lengths of the other two sides. Okay. So this is the triangle inequality. Which will be very useful. It's something that you use all the time in analysis. So we'll see a lot of it. I've probably said this before, but I have a friend who hates the triangle inequality because to him it represents a sort of a philosophy of defeat. You see, in the kind, what he likes to do is get exact answers. And for the most part, this is not possible. In analysis, you don't try to get exact answers. You try to get like some sort of control over the size of something, like good enough control. But he wants exact answers. And so, once you invoke the triangle inequality, you've given that up. Right? You've said, I cannot do it. Right? So, yeah. Okay. So let's. Okay. So take 1 minute and write down a proof of D. Why is D obvious? So proof of D. Right. So say that Z equals A plus BI, right? A comma B. Right. And write down why that's simple. Okay, so turn to your neighbor and say, it's simple, because? Okay, so what's the point? What's the absolute value of R of the real part? What do I rate for that? That's the absolute value of A, right? This is the real part, this is the real part. And what we're trying to show is that it's less than or equal to the absolute value of, the modulus of Z. Well, what's the modulus of Z?
Square root of A squared plus B squared.
Yeah. The square root of A squared plus B squared.
And square both that.
Yeah. So, well, right, let me rewrite this A on the left-hand side as the square root of A squared, right? The absolute value of A is the same thing as the square root of A squared. Well, we're trying to show that the square root of A squared is less than or equal to the square root of A squared plus B squared. Well, that's true. We want to show that this is true, but that's obvious. Now for the despised triangle inequality. So proof of the triangle inequality. You say, okay, we want to show that that this number, this positive real number, is less than or equal to this positive real number. Okay, and so you use a fact. So fact, and it's an easy calculus fact that if you have two numbers, if you have positive numbers then b is bigger than a is equivalent to saying that a squared is less than b squared. Right? Right? If a is less than b, then a squared is less than b squared. If a squared is less than b squared, then they've got to have this relation, right? So something like this. If a and b are positive, then these two facts are equivalent to each other. So this gives us this says that if we want to show that this is less than that, we can show that the square of this is less than the square of that. Okay. Right. So it suffices to show that the square of the left side is less than or equal to the square of the right side. Okay, so this is a pretty usual trick. Okay, so let's do it. Say, okay, well, the square of the left side, right? The square of the left side is, this is z plus w bar to the everything to the 1/2 squared, right? So I can just get rid of those guys. Right? Everybody okay? Right? Because remember, the modulus of something was z bar to the 1/2. Right? So I'm looking at the square of it, I just get this guy times this modulus. Okay? So then we write it out. Okay. So this is zz bar plus wz bar plus zw bar plus ww bar. Okay. Okay. Which I'm going to rewrite as the modulus of z squared, and over here the modulus of w squared, modulus of w squared. And I notice here that zw bar is what? Zw bar is going to be z bar w bar, but w bar is w, right? So I get z bar w, right? Because when you reflect it back, you come back to the original, right? So w complex conjugate is just w. Okay. So right. So this and this are complex conjugates of each other, right? If I take the bar of this, I get this, right? So I'm taking something and I'm adding it to its complex conjugate. We saw earlier that you get twice the real part, right? You get twice the real part. So you get this thing here, these guys together are going to be twice the real part of zw bar.
And would that be the same as the real part of w times z bar?
Yes, yes. Yeah, because that's a conjugate of it,
Yeah.
right? And if they're conjugates of each other, well, the real parts are going to be the same. Okay. Okay. But remember the thing we just showed. We just showed that the real part, the absolute value of the real part, is less than or equal to the modulus, right? Right? And of course, the absolute value of a number, of a real number, is bigger than or equal to the number itself, right? Right? The absolute value of -5 is certainly bigger than or equal to -5, right? Okay. So I notice that I'm going to take this guy and I'm going to say, well, that's less than this z, right? This thing is less than the modulus of z w bar, Okay. Right, so I get this plus this, right? And you see what that is, right? That is the same thing as z plus modulus of w, quantity squared. Right. Because I can because the absolute value of the product, I can split those up, and the absolute value of the complex conjugate is the same thing as the absolute value of the addition. Eric?
Shouldn't it be less or equal to?
Yeah. Thank you. Okay. And so altogether, what do we get? We get that the square of the modulus of the sum is less than or equal to the square of the sum of the moduli, right? In other words, that implies that the modulus of the sum is less than or equal to the sum of the moduli, which is what we want. Okay. Okay. So there's nothing, there's only two things going on here. One is this trick that we pulled, right? That you instead of trying to get this inequality, you can take the squares and do that, right? And the other thing that's involved is this simple fact, right? That the size of the real part is less than the size of the object. Okay. Any questions? Any questions? Cody? Okay, we've got 5 minutes and a little bit. Don't know if we can manage the Cauchy-Schwarz inequality, but let's see if we can. So there are, I think, hundreds of proofs of the Cauchy-Schwarz inequality. Rudin has chosen in his normal fashion sort of a very dense, sort of slick one. So Cauchy-Schwarz inequality says the following, that if you have a bunch of complex numbers, so you have complex numbers AI, so A1 through AN, B1 through Bn, that are all complex numbers, and you look at the sum of the squares of the moduli of the AI times the sum of the squares of the moduli of the BI, then that's bigger than or equal to the magnitude of the sums of the squares of the AI times the complex conjugates of the BI. Okay, so you've probably seen something like this back in multivariable calculus, but not with complex numbers, but with real numbers, right? With real numbers, you have some vector, right? A1 through AN. You have some other vector, B1 through Bn in Rn. And you have this thing that the dot product, right? A dot B, the size of the dot product is less than or equal to the magnitude of A squared times the magnitude of B squared. I'm sorry, squares on it. So let me take off the squares. Sorry. There should be a square here. Sorry. Okay. So I don't know. I'm hoping that you've seen something like this back in multivariable calculus, right? That the size of the dot product is controlled by the product of the magnitudes, right? And you proved it in a geometric way back then, right? You said, well, the dot product is the product of the magnitudes times the cosine of the angle between. The cosine of the angle is less than or equal to 1, and so you get this thing, right? Right? But this is something. Now we've left the real numbers behind, right? We're not in the real numbers anymore. Okay. So Okay, but this is some sort of analog of it. Okay, so Reardon gives a very terse proof. He says, well, okay, first off, without loss of generality, we can let A be, let A be the sum of the sum of the moduli of the AJ squared. Let B be the sum of the moduli of the BJ squared. Let C be the sum of the products of the AI against the BJ conjugates. Okay.
Is that just the conjugate on B?
Yeah, conjugate on B. Okay. He says, okay, well, without loss of generality, we can assume that B is bigger than 0. Yes?
In the original equation,
Yeah.
what is supposed to be I and what is supposed to be J?
They're all I's.
Okay.
These are all I's. These should also all be I's. It doesn't matter, right? They're all, these guys doesn't matter. These guys, it does matter. This should be AI, BI. Okay, without loss of generality, we can assume that B is bigger than 0, right? Because if B equal, you know that B is going to be greater than or equal to 0. If B equals to 0, then that would mean that, what? All of the B's are 0, right? Well, if all of the B are 0, then the statement is trivial to prove, right? You got 0 is less than or equal to 0. Well, that's true. Right? Right? So we don't have to worry about the case, right? We need not worry about the case B equals 0. We assume that B is greater than 0. Okay. Yeah.
Should there be a squared on C?
I don't think so. I don't think so. Yeah. Okay. Okay. So I think we don't have time to do it. So we'll start off with this. We'll start off with this next time.